I don't know. What do I know? Well, here we are. So we've reached the Euclidean algorithm in Keith Conrad's Blurb, Gaussian integers. Actually, we're not quite there. I have a couple definitions. So here's the definition. For non-zero, alpha and beta and the Gaussian integers, all right, the greatest common divisor, which I'll abbreviate as GCD, of alpha and beta. And did I just say the? I shouldn't say the. I should say a greatest common divisor of alpha and beta is a common divisor with maximal norm. That's what he said. I'm not entirely sure I believe that. So I have this like nagging feeling that should be minimal norm. But perhaps I'm wrong. Okay. Definition. When alpha and beta have, I should say only have, unit factors in common, we call them, well, let me just say, they're relatively prime. All right. Now for the Euclidean algorithm. Here it is, theorem. He says let alpha, beta be Gaussian integers with non-zero. Then he just says recursively apply the division theorem that we talked about last time, right? And he says, starting with this pair, make the divisor and remainder in one equation, the new dividend and divisor in the next, provided the remainder is non-zero. So I'll just say as follows. So here's the deal. We write alpha equal to beta gamma 1 plus rho 1, right? And what's the deal? The norm of rho 1 is less than the norm of beta, right? In fact, we proved that it can be, we can pick it less than 1/2 the norm of beta, remember? The argument we gave last time. Then next up, you put rho 1 down here, and you divide by, how's it go? Excuse me, don't put rho 1 down there. How's it go? You put beta down here, right? And then you find, divide rho 1 into beta, and you get it rho 1 times gamma 2 plus rho 2, right? Where the norm of now rho 2 is less than the norm of rho 1, right? Because now norm of rho 1 is the dividing number here. And then you bring the remainder down, rho 1, and you pick, find a quotient gamma 3. That gamma 3 times rho 2 is when you add a remainder 3 to that, you get back to rho 1. And of course, the norm of the third remainder has to do what? Has to be less than the norm of the second remainder, right? Now, since the norm is finite, right, and the norms of these remainders are strictly decreasing with each step, this process must terminate, right? And so eventually, you get the norm of, let's say, the k plus 1th remainder equals to 0, then, you know, whatever you had before that, let's say rho k equal to rho k minus 1, gamma, how's it go? K, that's the counting, right? Oh, wait a minute, no. Well, sorry, gamma sub gamma, I don't know what I'm talking about. Gamma sub k, I think. Well, that seems right. Oh, I'm sorry, it should be k plus 1 here, right? K plus 2, yeah, there we go, that's better. And then plus what? Rho, well, the one before k plus 1 would have...
No, k plus 2, it's the same as the gamma.
Oh, just a second, I'm starting out. I'm trying to write the one right before this. So like I want to write the rho k equation. You know, gamma, rho, the one right before the remainder is 0. You know?
So if that row is k, gamma has to be k, and rho has to be k minus 1.
And then over here we have rho k minus 2. K minus 2, right?
Yes.
The point is, here, this is the last what? Non-zero remainder, right? That would be the last non-zero remainder if the k plus 1th one was 0. I'm just saying, I mean, like, just let's use that language. Then how can you tell me how do the remainders relate? Right, so you got like norm of beta is greater than the norm of rho 1, right? Is greater than the norm of rho 2, is greater than dot, 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 is greater than the norm of rho k, right? And what's below that? Well, the norm of rho k plus 1 is 0, because the norm of 0 is 0. So he says that the common divisor of alpha and beta is the common divisor of maximal norm. But goodness, folks, I think it's the common divisor of minimal norm. Because, like, what we've learned, it's the same story as we had before. The greatest common divisor is, in fact, going to be the last non-zero remainder in the algorithm. Okay? So, that's going to be the GCD in this story, right? And the thing is, you can solve every one of these for like alpha minus beta gamma 1 equal to rho 1, etc. Right? So if you have a common divisor of alpha and beta, what? It's also a common divisor of the remainder. And that continues at each step down here. So the remainder is always a common divisor of alpha and beta. Right? So the last non-zero remainder is also a common divisor of alpha and beta. And we would argue, in fact, that it's the greatest common divisor, in fact. So I think that has to be minimal norm. Unless I'm missing something stupid here. Maybe just a typo, I guess. I think we'll see that play out in numerical examples here. So, all right, so here's example 4.4. Here we have alpha equals to 32 plus 9i, and we have beta equal to 4 plus 11i. All right? Now, let me show you how you can do this in a kind of like lazy way. Go to Wolfram Alpha, all right? And you can try like parentheses, what is it, 32 plus 9i divided by what?
4 plus 11i.
4 plus 11i. Now, of course, this could all be done by hand, right? But if you're like me, there's about a 10% chance you're going to make a mistake. which is then very annoying. Anyway, so the result is, well, that is not helpful. Curses. I need to, decimal, yeah, I want the decimal approximation. Fine, so I got like 1.65, blah, 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 plus 2.30 I. So like 32 plus 9i divided by 4 plus 11i is approximately, well, I mean, I can give you the exact result. It's 227 over 137 plus I times minus 316 over 137. Now that doesn't particularly delight me, although I guess you can see that this is like 1 plus some number over 137, right? And, oh goodness. I tell you, let me stop this. The whole point was to make this easier. So this is approximately, I just have a bad memory, 1.65 plus I times what? 2.31. All right, so that suggests to me that we should use gamma equal to, I don't know, 2 plus 2i. Is that what he uses? I'm not sure, actually. He uses 2 minus 2i. He uses a negative here. I haven't lost. How did I enter it?
Yes, where did you go to?
wolframalpha.com.
Yes, sir, there should be a bar on the top. Wolf, RAM, RAM, alpha. I'm in there, I didn't know which like that.
Just the main thing, like it's not a, just right there.
Just enter, oh.
Just like literally parenthesis 32 plus 9i, close parentheses, divide, parentheses, 4 plus 11i. That's all I did. No. It's nothing fancy. That's the beauty of the Wolfram Alpha. So you see, this calculation shows me that I should choose my first quotient as 2 minus 2i, which is indeed what he does in example 4.4, without explanation, of course, because if you explain these details, this blurb would not be a blurb anymore. It would be a book. And it would not be an interesting book either. So let me get to it. Again, I'm not going to go through all the calculations because, frankly, they're just not that interesting. But here they are. 32 plus 9i is equal to 4 plus 11i times 2 minus 2i. And then what's left over actually is 2 minus 5i. So 2 minus 5i is the first remainder. Then we have 4 plus 11i. You can do the same thing again. 2 minus 5i is now the dividing number. The quotient, the second quotient is actually minus 2 plus i. Second remainder is plus 3 minus i. All right. Then you got 2 minus 5i. You bring that down. You get 3 minus i. That's the dividing number. The next quotient is 1 minus I. The next remainder is minus I. At this point, if we're just after calculating the greatest common divisor of these two numbers, we're done, because we've gotten to a unit. Remember, the units in the Gaussian integers are what? Plus or minus 1, plus or minus I. Them's your 4 units. All right? Now, the next step is, 3 minus I equals to, well, how's it go? Sorry, I did it wrong. He's like, 3 minus I is minus I times, well, goodness gracious. Thank you. 1 plus 3 plus 0. So this right here, last non-zero remainder, right? But I think that's, is it the common divisor with Maximal. I guess it is the common divisor with maximal norm. I'm thinking wrongly here. Like it's easier to see if let me just. It's just my bad thinking. The fact that this is well. He says maximal. I'm going to have to. Sorry, guys. This is bothering me, but it's only started to bother me about the last half hour, so I haven't had a chance to investigate it thoroughly. You know. All right. Let me not ruin this lecture with this nonsense. I will look into it after class and explain to you the error of my internal thinking, because odds are very high that Conrad is correct. Like. Very high. All right. Okay, so this shows you that alpha and beta are relatively prime because their greatest common divisor is a unit. All right. Now, so I would like to show you now the vector Euclidean algorithm for the same example. Okay. I'll do it over here. I need a little more room. This will illustrate that Bézout's theorem still works in here. All right. So here it is. Again, alpha 32 plus 9i, beta 4 plus 11i. All right. So we'll start with 32 plus 9i, come on, comma, 4 plus 11i equals to alpha beta, right? I always state that at the top of my vector Euclidean algorithm just to set the terms and conditions of the thing, you know? Now, that's like I used A and B for before, right? Remember I used A and B previously? I was using alpha and beta to make it weird. So 4 plus 11i, and it turns out the remainder is 2 minus 5i. All right? So it's basically following that calculation. How did you get 2 minus 5i? Well, remember beta goes here. And how did you get this 2 minus 5i? Well, you took alpha and you subtracted 2 minus 2i of it. 2 minus 2i of beta, right? Oh, I wrote it in a really weird way in my notes. Anyway, moving on. So then, all right, next, we've got, how's it go? 2 minus 5i comes down, right? And it turns out the remainder of the next one, again, you'd have to do more calculation on the side. It's like not like this is just obvious, right? Each step, you got to go through the thing I did with decimals to like see it, right? Each step you need to do this kind of calculation to figure out what the quotient should be, all right? And anyway, here it is. So we have alpha minus 2i beta. And then how did we get the second thing? Well, how did we get this 3 minus I? Well, we did beta minus parentheses I minus 2. And then of this thing, right, which was alpha minus 2i minus 2 beta. All right. And I won't go through the details, but if you do the algebra carefully, that simplifies to alpha. And I change this to a plus. If I change it to a plus, it becomes 2i minus 2, yeah? That's easy enough to see. But then what is not as easy to see is what that simplifies to is 6i minus 1 times beta plus 2 minus I times alpha. All right. Next up, we bring down the 3 minus I. And the remainder at this point, thankfully, is minus I. Yay, final step, right? And so we bring the 6I minus 1 beta plus 2 minus I alpha over here. Doesn't really matter. What's more interesting is what goes over here. And so we're going to do alpha plus 2 minus 2I minus 2 beta. All right. Minus what? Minus 1 minus I times this mess. And you simplify. And what you get is, I'm going to call this thing Pac-Man. So you get Pac-Man, which I still don't care what it is. Whatever it is, whatever. The more interesting thing is what goes over here, which simplifies to 3I alpha minus 7 plus 5I times beta. All right? And just like before, the vector Euclidean algorithm gives us this equation. It gives us that minus I is equal to 3I alpha minus parentheses 7 plus 5I times beta. So that equation shows you that the GCD of alpha and beta is equal to minus I. However, it's not the only thing you could say. You could multiply this equation by I. What would happen? Multiply this equation by I get 1, right? Because I squared minus I squared is 1. 1 equals to minus 3 alpha minus 7I minus 5 times beta, which shows you what? Well, this indicates that the GCD of alpha beta is equal to 1. So notice that the greatest common divisor, the reason we said a greatest common divisor is because it's not unique. The greatest common divisor is only defined up to a multiple of the units in the Gaussian integers. So unlike our usual positive integer study where we have a unique greatest common divisor, here we do not, but that's not a problem either. So this is not in Conrad, but I wanted to show you this. This was my second try. The first time I made a stupid mistake, like 2 different places, and it all crashed down. You got to be really, really careful with these calculations. That's why I'm encouraging you to use Wolfram Alpha or something, whatever, works best for you. But. All right, so the argument that the last non-zero remainder can be is the GCD. It's much akin to the arguments we gave before, in the integers. But all right, anyway, so here's example 4.5, and here he wants to show 4 plus 5I and 4 minus 5I are relatively prime. All right, so here goes. 4 plus 5I is equal to 4 minus 5I times I minus parentheses 1 minus I. And you can check that out, if that's reasonable, right? So you're going to get a 5 from the first product because you get minus 5 times minus 1, right? And then you're subtracting 1, so you get 4. 4 equals 4, good. And we also get 4I from the first term, and we get a plus I from the last one, so you get 5I, right? So it checks. And you can also take the norm, right? The norm of 1 minus I is 2. The norm of the dividing number is what?
1.
No.
Oh, wait, the dividing number.
Yeah. So 41. So definitely 2 is a legit, if it has norm 2, it's definitely small enough to be considered like a legit remainder, right? Because it's definitely smaller than 1/2 of 41. All right, next up, 4 minus 5i equals to, here's how it goes, minus 1 minus I times minus 4 minus I, all right? So this shows you, once you get to minus I, you know that the next one's going to be 0. All right, once you get to a step where you have units, the next one will be 0. We don't need to really write it down, okay? He usually does, to his credit, but we don't need to. Anyway, that already shows that the GCD of 4 plus 5i and 4 minus 5i is equal to minus I, right? Which shows you that their greatest common divisor is a unit, right? So that means that there's not a common divisor that is larger, like a non-unit would be things that have norm larger than 1, right? And so the fact that it has a norm, that the unit is the greatest common, the divisor of maximal norm, that shows you that there's not a divisor that's bigger than a unit, so to speak. I don't want to say bigger than a unit, but norm larger than a unit, let's say, okay? Now, can you guys see, question, could you see how to write 1 as, something like something times 4 plus 5i, fill in the blank, right? Plus something else, fill in the blank, 4 minus 5i. I think with this one, you could like just straight eyeball it,
Yeah.
Maybe.
Oh, find two numbers that multiply. Oh, it's the I know what this is. What was this called? What equation is it called?
Bézout?
Bézout's.
Yeah. Tell you what, I will show you. So I haven't emphasized this method, but I'll show you this. This is the method Conrad emphasizes, which is back substitution, right? So what he does is he takes this equation right here, he solves it for minus I, right? And then what? And then he takes the equation above, right, this one, and he solves it for this guy. And he plugs that into here. So if you solve this one for that, what do you get? You get 4 minus 5i times I minus 4 plus 5i, right? All times minus 4. So what does this give us? This gives us 1 plus I times 4 minus 5i plus 4 times 4 plus 5i, right, is minus I. Which then, if you multiply through by I, you can get the equation of the one that I was trying for us to just eyeball. So 1 multiply by I, yeah. And so we get I minus 1 times 4 minus 5i plus 4i times 4 plus 5i. I think my request for you to just kind of like just eyeball it and just tell me what you should fill in the blanks, I think maybe that was a bit much to ask, yeah? Factoring complex numbers, it's a little bit trickier than real numbers, isn't it? It really is. All right. So a corollary. Uh, 4.7. It says for non-zero alpha and beta in Zi, right, let delta be a GCD produced by Euclid's algorithm any GCD of alpha and beta is unit multiple of delta. I claim this, right? I've already claimed this. I've been saying this in the numerical examples, but I haven't proved it yet, have I? Here's the proof. He says let delta prime be a GCD of alpha and beta from proof of the Euclidean algorithm. Delta prime must divide delta because delta prime is a common divisor of alpha and beta, right? So what does that mean? We can write delta prime equal to what? No, delta rather. Got to get my thing straight. Delta is equal to delta prime times what? Times some other Gaussian number gamma, right? And then, as is many of these proofs, we take the norm. So the norm of delta is the norm of delta prime gamma. But remember, the norm is multiplicative, as we proved last time. So we get that, right? But what do we know? We know that the norm of delta, right, is greater than or equal to the norm of delta prime because it's what? It is the GCD, which is maximal, right? Maximal norm. So you look at that equation. What does that force? What does that force the norm of gamma to be? Or look at that inequality rather. See, remember that the norm is an integer. So the only way that an integer can be smaller than or equal to a product of another integer in itself is it.
The norm of delta prime divides norm of gamma.
That is true. The norm of delta prime divides the norm of gamma. Very true. But more to the point, the norm of gamma rather, has to be equal to 1 here. And remember, the elements with norm 1 in the Gaussian integer are the units. So this proves the theorem, the corollary rather. All the GCDs, they're unit multiples of each other. All right? So, so I hate to erase this at the moment. Well, I guess I can write over here. So we're now into section 5, which is Bézout's theorem. And here it is, theorem 5.1. Let delta equal the GCD of alpha and beta, right? Alpha comma beta not equal to 0 in the Gaussian integers. Then delta is equal to a. Oh man. Oh yeah. Oh, I'm bad. Alpha x plus beta y for some x and y in the integers. So the proof is really just the back substitution I just described. All right. The proof is that you can go to the division algorithm and you can take the last non-zero remainder and you can solve it for the difference of the next to last non-zero remainder minus the quotient times the thing, and then you can plug in the equation above, and then you can plug in the equation above that. Basically, you can just do substitution down the stack of the equations we get for the division algorithm. So that's, I mean, he writes it in a nicer paragraph, but that's essentially it. And of course, pragmatically speaking, we can use the vector Euclidean algorithm as a means to calculating the linear combination, right? Like, example that we just calculated was, minus I equals to, what was it, 3I alpha minus 7 plus 5I rather, beta, when alpha was something ugly, wasn't it? 32 plus 9I, and beta was 4 plus 11I, right? So just to try to make sure we're not talking past each other here, x was literally this 3I, and the y in this context was, minus 7 minus 5I, right? So that was the x and y which exist to build the GCD, a GCD. If I slip up and say the GCD, understand it is just because it's very unnatural for me to say a GCD, as a linear combination of alpha and beta, a Gaussian linear combination. All right, and corollary to this, for 5.2, it says that alpha, beta, in Zi, all right, are relatively prime if and only if there exist x and y in Zi for which the alpha x plus beta y equals to 1, right? So I won't write down the proof to this, I'll just kind of talk through it. So if alpha and beta are relatively prime, then that means we can, by Bézout's theorem, write a GCD as a linear combination of alpha and beta, right? Now if that GCD, that specific GCD is not 1, we can multiply it either by I minus I or minus 1 to make it 1. And multiplying through the linear combination we had for Bézout's theorem will then give us 1 is equal to alpha x plus beta y, like that. Conversely, if we know this is equal to 1, then we can argue that alpha and beta are relatively prime. That I'm less clear on. Let's see here. Well, here's what he says. Conversely, if 1 is equal to alpha x plus beta y for some x and y, then any common divisor of alpha and beta is a divisor of 1 and is thus a unit. So the converse direction is actually very not that bad, right? So here's the converse direction. I'll write it down. If alpha x plus beta y is equal to 1, and d divides alpha and d divides beta, then d divides 1. All right. But the thing is, if you divide a unit, we proved, I think, last class, that the divisors of units are themselves units. Right? Which again was something we reaped from the norm formula. All right. So in example 5.3, he shows, example 5.3 produces what I produced over here with the vector Euclidean algorithm. All right, so if you look at example 5.3, he uses the back substitution method to derive what I derived with the vector Euclidean algorithm. So I have said in your homework, use the vector Euclidean algorithm. If you prefer to use the back substitution method, you're welcome to. But as for me, I prefer the vector Euclidean algorithm. I don't know which one's worse or better, but okay. He has some lovely examples, which I'm going to. So he has example 5.4, 5.5, 5.6. He's, again, illustrating Bézout's theorem calculation, all right? And actually, examples 5.4, 5.5, 5.6, they mirror the examples I've skipped between this lecture and the last. Basically, he's unsubstituting the division algorithms he went through, I think, if I remember right. Anyway. Okay, so let's see here. So this brings us to corollary. So we're getting into the divisibility in Gaussian integers now, right? Like we've been sort of doing some of it, but now we're really getting into some of the meat. Well, I don't know. I mean, these are actually pretty easy. Alpha divides beta gamma in Zi with alpha and beta relatively prime, period. Then sometimes you see things written like this. This is just kind of a, in my opinion, slightly awkward way of writing an if-then statement, you know? So here's the if, and then there's the then, next sentence, you know? So you guys tell me, what does this mean? What do you think the conclusion is here? If you have alpha and beta relatively prime, right? That means that alpha does not divide beta, right? So it has to divide the other thing. That's the way to think of it. Then alpha divides gamma. All right. And let's go through the proof. I'm partly going through this proof as a help to you guys because I've asked you to prove the next corollary in your homework. And I just want to show you that you can literally go back to our work in the integers and lift the format of the proof, replacing integers with Gaussian integers. It's the same argument. So this is worth our time. Let's go through it. So he says, so we're going to suppose alpha and beta and gamma are the Gaussian integers with alpha comma beta equal to 1. This is his notation for GCD. So let's suppose that the alpha and beta are relatively prime, right? And what else do we assume? We assume that alpha divides beta gamma, right? So he says set beta gamma equal to what? Equal to alpha kappa for some kappa in the Gaussian integers, right? We can do that because that's the definition of divisibility, right? What else do we know? There exist what? There exist x and y in the Gaussian integers such that what? 1 is equal to alpha x plus beta y, right? By our corollary 5.2 we just put up there, right? They're relatively prime, so you can write 1 as a Gaussian integer linear combination. All right, then what? Multiply by gamma, right? That gives us gamma equals to, let's see here, gamma alpha x plus, gamma beta y. But we already know what gamma beta is what? Remember gamma beta up here? It's alpha kappa. And hey, we're done. because you can factor out alpha, right? So you got yourself a gamma x plus a kappa y, all times alpha. Therefore, alpha divides gamma. This is literally the same proof we gave in the integers. All right. So next up, we have corollary 5.8. So these ones I'm not going to prove. I'll leave the proof of these ones to you guys. If alpha divides gamma and beta divides gamma with alpha and beta relatively prime, then, well, alpha beta divides gamma. All right. Corollary 5.9 says that for non-zero alpha, beta, gamma in the Gaussian integers, right, with alpha and beta relatively prime, alpha and beta are each relatively prime, not to each other, but to gamma. So alpha, GCD of alpha and gamma could be 1. The GCD of alpha, beta and gamma can also take into be 1. All right? So, you're cracking me up. Sorry. I don't know, but I appreciate the devotion to of slapping yourself to keep yourself awake to take notes. Like that's hardcore. Let's see here. So then here's the deal. If and only if alpha beta is relatively prime to gamma. So the product of alpha and beta being relatively prime to gamma can be interchanged with alpha being relatively prime to gamma and beta being relatively prime to gamma. This is corollary 5.9. So at this point, he points out that there are multiple ways to describe the greatest common divisor of non-zero integers. He mentions, he's like, well, it's the largest common divisor of a and b. That's the usual definition in the integers, right? He says you could also say it's the positive common divisor which all other common divisors divide. All right. It's the smallest positive value of ax plus by, with x and y being taken from the integers. He said, or you could say it's the positive value of ax plus by with x and y taken from the integers, which divides all other values of ax plus by. And then he says, like, the corresponding characterizations in the Gaussian integers would be a common divisor of alpha and beta with maximum norm. That's the definition. A common divisor which all other common divisors divide. A non-zero value of alpha x plus beta y with smallest norm. Or a non-zero value of alpha x plus beta y, where again x, y are taken from the Gaussian integers now, which divides all other values of alpha x plus beta y. And he leaves proving the equivalence of these conditions up to the interested reader. So, I don't know. I think it's interesting. So this brings us to the next section, which is really the... So there are other number systems that are very, very much like the Gaussian integers. And I think up to this point, the things we've done for the most part can be mimicked in other systems. Well, okay, that's not quite true. Some of them don't quite allow for a division algorithm. That's like the problem, actually. So I probably shouldn't quite say that. But there are other systems, anyway, which don't have this unique factorization. And unique factorization is actually really critical to the arguments we'll see as we apply the Gaussian integers to solve interesting problems. All right, so unique factorization he says for, excuse me, this is lemma 6.1. For alpha not equal to 0, any divisor of alpha whose norm is 1, or an alpha is a unit or a unit multiple of alpha. So let's go through his proof. It's not too long. He says if beta divides alpha, right, then, and the norm of beta is equal to 1, then beta is either plus or minus 1 or plus or minus I, right? It's a unit. Because if the norm of beta is 1, it's a unit from last time. All right? Now, he says, if on the other hand, beta divides alpha and the norm of beta is equal to the norm of alpha, that's the other case, right? He says, consider the complementary divisor gamma where alpha is equal to beta gamma. Okay, well then, there exists gamma in the Gaussian integers, right? Such that what? Such that alpha is equal to beta gamma, right? He says take norms of both sides and cancel the common value n sub alpha. So, okay, so an n of alpha is equal to n of beta times n of gamma, right? And what's this say? Remember, we're assuming what? N of beta equals to n of alpha. Thus what? Did you see it? So if these guys are equal, that means this and that are equal. So we can cancel them. And we again have the norm of something equals to 1, which implies that gamma is plus or minus 1 or plus or minus I. It's a unit, right? Which implies what? That alpha is equal to plus or minus beta or plus or minus I beta, which is to say that alpha is a unit multiple of beta. So that's how it goes. Now, he gives a warning. He says lemma 6.1 is not saying that the only Gaussian integers whose norm n of alpha are plus or minus alpha and plus or minus I alpha. For example, here's a cautionary sort of counterexample. Not a counterexample, but it's a, don't overextend what this is saying, right? So if you look at the norm of 1 plus 8i, and you look at the norm of 4 plus 7i, right? These guys are definitely not what? Those are definitely not unit multiples, right? But their norms are equal. See, because this is 65, and this is 16 plus 49, which is also 65, right? So it is, of course, possible to have the norm of two Gaussian numbers be equal, and yet they're not unit multiples of one another. However, if, notice the condition here is not just that they have, norm alpha. The key is it's a divisor, right? So we're looking at numbers which divide alpha. This does not divide that, all right? So, okay, so All right, so in some sense, these things that Lemma 6.1 addresses, these are sort of the trivial cases, right? So the analog in the integers, so let's see here. You know, you've got 12, right? 12 is what? Well, it's 3 times 4, right? But what else is it? Oh, have I chose poorly? 15. My bad. Yeah, sorry, bad example. Bad example. 3 times 5 is the one way we could factor it, right? But there's another stupid way we could factor it. Well, it's not stupid. Minus 3 times minus 5, right? There are 2 other, actually those are both interesting factorizations, I would say, of 15, right? What are sort of uninteresting factorizations of 15? Well, how about 1 times 15, right? And so in some sense, these we don't really count as factorizations, do we? Because we want the factorization to be, I would say 3 times 5 and minus 3 times 5, those are interesting. But the 1 times 15 and the minus 1 times 15, that's something we don't really want to count as a factorization of 15, right? Because you can do that for any number, right? And we'd like to describe when a number is what we say is composite, right? 15 is a composite number. In contrast, you have numbers which are not composite, right? Like primes. So 7 is 7 times 1, and it's minus 7 times minus 1, right? But we wouldn't say that that proves that 7 is composite, right? Because one of those is a unit. So the same story goes for the Gaussian integers. Let me write down the definition. .2. It's page 12 of Conrad's Blurb, if you're wondering. Let alpha be a Gaussian integer with the norm of alpha greater than 1, right? In other words, it's saying, what is it? What's another way you could say that? Pick a Gaussian integer which is not a unit. That's all it's saying. Gaussian integer which is not a unit. We call alpha composite, all right, if it has a non-trivial factor. So trivial factors, what are trivial factors? Trivial factors of alpha include plus or minus 1, plus or minus I, plus or minus alpha, plus or minus I alpha. These are the trivial factors of alpha. All right. So non-trivial factor is something other than these. All right. So he says if we write alpha equals to beta gamma, all right, then he says the condition 1 less than, I lost my place, n of beta less than n of alpha is equivalent. Well, this can be interchanged with, and this is the way I think about it, n of beta greater than 1 and n of gamma greater than 1. I mean, this right here is I think, a key way to think about it. It's a